I'm presenting on behalf of Michael Rietzler because he became a father recently, so therefore he cannot be here, but I'm happy to present for you. So this work was done with my colleagues from Ulm University in Germany, and we tried to combine pseudo-haptics with muscle input. So let's jump right into it. So when we look at virtual reality like it is today, we see that we have very high resolution displays that provide lots of details. We have high visual fidelity, which enables convincing 3D graphics. And we have very sophisticated hardware in terms of head-mounted displays and controllers, which are robustly tracked with 6 degrees of freedom in space. So having this hardware allows us to for novel ways of directly interacting with virtual objects and virtual environments. But one of the problems that still exist in consumer virtual reality is that haptic feedback is mostly limited to the vibration of controllers. So to illustrate the problem, I have a little video. When we lift virtual objects, it does not matter if they are light or heavy. Therefore, grabbing a cup, a table, or even a whole wall just all feels the same. So, of course, we're not the first to tackle this problem. We've seen a lot of nice work during the last days and also in the past. And all of those approaches can be categorized into the following 3 categories. We have hardware-based feedback, for example, pulley systems, robots, or exoskeletons that can provide really nice feedback, but one of the problems with them is that they are often special purpose, they are large and complex, and they are not really applicable to consumer virtual reality as we have it right now. So then we have passive haptic feedback, which makes use of existing passive objects in their surroundings, like the project by Simeone et al., which uses the objects inside a room and mapping them to a virtual environment. So this also provides good feedback, but it's constrained by the available physical properties. Third, we have pseudo-haptic feedback, which is very low cost and flexible because it only uses visual displacement and no hardware. And that is used to convincingly communicate friction, stiffness, or directional forces, such as the approach that we presented in KITE last year. So a problem with this redirection is that it leads to a loss of control. So what we wanted to create with this project is a system that does not need any complex hardware or is constrained by the physical properties, but also provides more control to the user. So therefore, we combined the previously presented pseudo-haptic feedback approach and added muscle tension as an additional input channel. So let's first explain the pseudo-haptic feedback approach. So usually when we grab objects in VR, they lose their physical properties, have no weight, and are bound to the tracked controller position. Now in our approach, the virtual object retains its weight, so gravitational forces apply and the object is pulled downwards. The now existing offset between the object and the controller position is now used to calculate an offset force, which is pulling from the object towards the controller. So this means the heavier the virtual object is, the larger the offset where both forces are equal get. Or in other words, to lift a heavier object to the same height, we have to lift our arms higher. So when we now add muscle tension as an input, we introduce an additional muscle force, which is pulling also in the direction of the offset force. And when the muscle tension increases, the muscle force is scaled accordingly and effectively reducing the offset and moving the virtual object towards the controller. So this approach does not only work for weight, it's also applicable for resistance of objects. So when reaching through virtual objects with relaxed muscles, only the offset force applies. But when we now tense the muscles, the offset is reduced and we are able to apply higher forces to that object. To implement that concept, we used standard consumer hardware, namely the Oculus Rift as the virtual reality headset, and the Mayo armband from Telmic Labs with its 8 EMG sensors. So this was worn on the upper arm of users, measuring the biceps and triceps of them. We used only the largest factor of the 8 measurements provided and filtered them for a smoother signal. And to calculate the applied muscle force, we used this formula. Let's take first a look at the inner term, where M is our current measurement, and min and max are values that we retrieved during a 2-point calibration of relaxed and fully tensed muscles before the experiment. So this gives us a value between 0 and 1, which is then multiplied by 110 Newton, which is approximately what a human can hold with one arm. And the offset force O, which was introduced by the pseudo-haptic feedback approach. Of course, we wanted to test that system, and so we conducted a study in a virtual environment to test our system. And we choose a within subjects approach with the 3 conditions state-of-the-art, so no haptic feedback, pseudo-haptics approach alone, and pseudo-haptics combined with the muscle input. We had 21 participants belonging to a pretty much standard university sample, and as measurements we used the E2I questionnaire for enjoyment and immersion and 5 single item questions. So within each condition of the experiment, 5 tasks had to be fulfilled by the participants. So the first task was to push a wooden structure that it creates a bridge for them. The second task was to crank a big wheel to clear the path in front of them. Third task was to push open a double-winged wooden door, and followed by lifting the lid of a heavy chest, and finally lifting a golden dragon statue out of the chest. So let's get to the results. For every condition we had high enjoyment ratings, and the pseudo-haptic were higher rated as the baseline, but pseudo-haptics combined with muscle input was highest ranked, and the differences between them are significant. So interesting here is that we also see the lowest ratings for the pseudo-haptic muscle approach, and I will come back to that later. So in terms of immersion, we see no strong variations, but a tendency for pseudo-haptics combined with muscle forces to be rated the highest. So therefore we argue that this approach is able to increase immersion. Now for the single items questions, we found that the realism of physical constraints was influenced most by the introduction of pseudo-haptics. So both conditions that use pseudo-haptics are significantly higher rated as the baseline condition and achieve the same median score. For the feeling of manipulating real objects, it varied more, and we found the difference to be significant for all pairs, with the baseline rated lowest, followed by pseudo-haptics and pseudo-haptics combined with muscle force. The biggest variations that we observed were for the statement, "I could feel a resistance." So obviously we have very low ratings for the baseline condition that does not provide any haptic feedback, but also the condition with muscle input is rated significantly higher than pseudo-haptics alone. So for the statement, "I could influence the behavior of objects," the median ratings were equal for the baseline condition and the pseudo-haptics condition. But muscle input provides more control to the users, and therefore compared to the other 2 approaches, it is not completely passive, so that's probably why it was rated higher here. So last but not least, we let participants rate how much they liked the 3 approaches. And pseudo-haptics with muscle input was not rated higher as pseudo-haptics alone, and this can be explained because the baseline is basically having superpowers, and adding that approaches is an additional challenge, so it hinders users to achieve their goals as fast as possible. So beside those quantitative results, we extracted further insights based on the informal feedback of participants during the experiment. So first, tensing the muscles without a real-world counterpart is something that not everybody is accustomed to, and it can feel strange at first. So before deploying such a method, you should provide a training for the users. And although users did not really have to lift heavy objects during our study, tensing the muscles is still exhausting, and therefore it should be used with caution and probably not for every single interaction, but only when it's helpful and appropriate. Muscle input introduces an additional challenge. So while normal VR feels like superpowers, this challenge can be a burden. And if the user just wants to achieve the goal as fast as possible, for example in a gaming setting, they won't like it that much, and this was reflected in the enjoyment and liking statements. So in terms of applications, this approach can either be designed very realistic by using a more complex calibration and an exact mapping of real weight and virtual weight, or real forces and virtual forces. Or it can be used as a game mechanic with different strength levels according to the character state or character development. So to conclude, our approach does not need complex hardware, and obviously it cannot substitute real haptic feedback, but using muscle tension as an additional input is a simple and effective solution to enhance pseudo-haptic feedback approaches. We showed that it can increase immersion and enjoyment, and it was rated more realistic and better conveys physical resistance of virtual objects. So muscle tension makes interaction more natural because users have to really make an effort and feel the weight of objects. So ultimately, it improves pseudo-haptic feedback by giving the users more control within the virtual world. So this brings me to the end of my talk. I was very fast, so maybe I skipped something, but because of that, I'm very happy to take the questions that still remain. Thank you.
So, thank you very much. We have plenty of time for questions.
Hi, I'm Harrison Allen from MIT. I was wondering if you've used this in conjunction with inverse kinematics, because I know that can also increase immersion in like these kind of experiences.
Sorry, can you repeat the first?
Yes, so have you used this with like maybe a full arm or full body as well?
Sure. Yeah, so now we only use it for the biceps and triceps, which is good for pushing and lifting objects. But of course you can increase it to other muscles. But then again, it gets more complex. You need some full body suit for the user. So what we wanted to do here is really use simple hardware, a simple solution that can be applied to consumer virtual reality. Yeah, thanks.
So I'll ask a question. You found some mixed results in terms of people's appreciation, and I think that some of that was probably due to, at least two factors strike me. In one, you mentioned trying to get the job done fast, and so there might have been a speed slowdown as a result of this. And the other one was a particular kind of application in what the goals that the user might have, and the goals might not have been to use their muscles. Yeah. So have you thought more about both the potential of speeding up the process, like what is making it slow, or slow enough for people to notice it? And then also, are there other applications you're looking at where the tensing of the muscles would be for a purpose other than immersion and enjoyment, like into itself?
Okay. Yeah. So for the first part, I think it's not only about the speed. It's also because they really have to make a physical effort. So it just gets more exhausting over time. So it's not just being slower; it's also having to make a greater effort. And the second part was
if there's other applications where the point might be to make physical effort, so the muscle exertion that is maybe problematic in this application would actually be one of the objectives, one of the intrinsic goals of the user. Like a workout application would be the obvious one.
Yeah, sure. It just helps to feel the weight of objects. So you actually have to do something to lift objects. So a workout application would be a nice.
I was wondering if there was one that was less obvious beyond that. All right. Any other? Okay. Oh, there's a couple more. How about right here and then back.
Did you try different placement for muscle measurement? I mean, now you're using arm, right?
Which kind of displacement?
Placement. I mean, maybe you can measure muscle around hand or.
Yeah. So because we started thinking about the weight of objects, we started at the biceps and stayed there. So we did not look at other muscles.
So I'm wondering about experiences, you or the people who tried it out for a longer term. So usually when we have in the paper, we have this short-term study, we get people in, they use it, they go out. But I think if you look at children, how long it takes them to sort of lift a cup without sort of spilling it, so till they get sort of the understanding of the feedback. Is there something, what US researchers, by trying it out probably many times before you really went in the study, is there a learning effect? Just to speculate on it, is it sort of something which we should look at, not just sort of this 1 hour where people try it, but sort of the longer thing that we may, if we stay longer and we have a completely different approach to haptics than we do that if we do the 1 hour study?
Sorry. Yeah, so I'm not an expert on EMG measurements, but I think there is a learning effect that you can maybe try to trick the sensor. But spending a lot of time you are. I'm not so sure about the second part of your question, so sorry.